All right, today we're going to do something pretty cool. We're going to crack a secret code. And the thing is, this code is hidden in plain sight all around us. It's a language written in numbers that, believe it or not, governs everything from simple puzzles right here on Earth to the grand cosmic dance of the planets. So yeah, let's dive right in. I mean, it sounds like a weird riddle, doesn't it? Fencing posts, flashing lights, planets aligning, what could they possibly have in common? But what if I told you that all of these seemingly random problems can be unlocked with one single mathematical key? Stick with me, because by the end of this, you're going to know exactly what that key is and how to use it.
Okay, first things first. Every code has its own alphabet, right? Its basic building blocks. Well, for the secret code of numbers, that alphabet is made up of things called factors, multiples, and, the real superstars of the show, prime numbers.
So let's kick things off with factors. The easiest way to think about them is this. They're numbers that can be packed neatly into another number. Take 12, for example. You can pack in groups of 2, or 3, or 4, or 6, and you'll have no leftovers at all. They just fit perfectly. Pretty simple, right?
Now, multiples are kind of the opposite of that. Instead of breaking a number down, you're building it up. Just think of a number's times table, stretching out forever and ever. So for 12, you've got 12, 24, 36, and on it goes. And that brings us to the real heavy hitters, the most important players in this whole code, prime numbers. Seriously, think of these guys as the fundamental units of math, like the indivisible atoms that all other numbers are built from. You just can't break them down any further, which, as you're about to see, makes them the absolute perfect tool for our decoding mission.
So the big question is, how do we actually use these prime atoms to figure out what other numbers are made of? Well, we use this really powerful technique called prime factorization. You can think of it like a personal DNA test for numbers. And this is where we get to one of the most incredible ideas in all of mathematics. It's called the fundamental theorem of arithmetic. Sounds fancy, I know, but all it really says is that every single whole number has its own unique prime code, like a fingerprint that belongs to it and only it. Our job? It's to find that fingerprint. And the way we do that is with something called a factor tree. Let's just do one together with the number 180. You can see it on the screen. We start by splitting 180 into any two factors. Here we're using 18 and 10. Now, neither of those is a prime number, so we keep going. We follow the branches down. The 10 splits into 2 and 5. Hey, both of those are prime, so we circle them. Then the 18 splits into 2 and 9. 2 is prime, circle it. And finally, that 9 splits into 3 and 3. And that's it. All the ends of our branches are now prime numbers.
Okay, so what do we do now? We just gather up all those prime numbers we circled at the ends of the branches. We write them out using index notation to keep it tidy. So the unique prime fingerprint for 180 is 2 squared times 3 squared times 5. And just like that, we've cracked its code.
So now that we can find the prime fingerprint of basically any number, we can use that information to create two master keys. These are going to be the highest common factor, or HCF, and the lowest common multiple, or LCM.
This slide is really the heart of it all. It shows how we use those prime codes to find both the HCF and the LCM, using 72 and 120 as our example. Let's start with HCF. Now pay close attention to the rule. You only look at the prime factors they have in common, which for these two are 2 and 3. And then you pick the lowest power for each one. Simple. Now for the LCM, the rule is totally different. You take all the unique prime factors from both numbers, so that's 2, 3, and 5, and this time you pick the highest power of each. You just follow those two simple rules, do the math, and boom, our answers are 24 and 360.
Okay, this is the one thing you absolutely have to remember, because it feels, well, kind of backwards. It's a paradox, right? The highest common factor uses the lowest powers, and the lowest common multiple uses the highest powers. I know, it messes with your head a bit, but trust me, burn this into your memory. It's the number one thing people get tripped up on, but it works every single time.
All right, enough theory. We've got our concepts down, we've forged our master keys. Let's go back to those puzzles from the very beginning and see how HCF and LCM can actually solve real-world problems.
So here's our first challenge. We've got this field, and we need to put up fence posts at equal intervals all the way around, including the corners. The question is,
What's the absolute widest, the greatest, distance we can put between them so they still line up perfectly?
You hear that keyword? Greatest distance that has to fit perfectly into both 450 and 330. That's a huge clue. It's screaming at us that we need the highest common factor. So we do our thing. We find the prime codes for both numbers, we look for the prime factors they have in common, that's 2, 3, and 5, and we multiply their lowest powers together.
And the answer is 30 meters! That is the biggest possible gap we can have between our fence posts for everything to line up perfectly. Puzzle 1 solved. Okay, on to puzzle number 2. We've got two lights. They're flashing at different speeds. What we want to know is, when are their cycles going to sync up again? When is the very next time they're going to flash at the exact same moment?
Okay, did you catch the keywords there? Next time together? That's our signal. It tells us we're looking for a point in the future where both of their cycles complete at the same time. We need the first multiple they share. In other words, the lowest common multiple. So we get the prime codes for 12 and 20, we grab the highest powers of all the unique primes, and we multiply them out.
And there it is, 60 seconds. They're going to flash together again in exactly 1 minute. Puzzle 2 solved. Are you starting to see how powerful this is?
So we've solved some puzzles here on the ground. But what's really mind-blowing is that this exact same logic, this same secret code, doesn't just work for fences and lights. It applies to the entire universe.
I want you to imagine 3 planets, all starting in a perfect line with their sun. But of course, they all orbit at different speeds. The question is, how long will it take before that grand cosmic alignment happens all over again? You know what? This is basically our flashing lights problem, just on a cosmic scale. We need to find the one point in time where all 3 of those orbital cycles sync back up. This is another job for our friend, the lowest common multiple. We find the prime codes for 4, 10, and 15, and, you know the drill, we multiply the highest powers of all the unique primes involved. And that grand alignment will happen in exactly 60 years. It's incredible, right? From fence posts to flashing lights to the alignment of planets, the very same secret code of numbers gives us the answer. So now you have the tools. You can see and understand these repeating patterns that are happening all around you, which really makes you wonder, doesn't it? What other invisible patterns are out there, all around us, just waiting for someone with the right key to come along and finally decode them?